So having done that, let's move on to this basic power flow equations. Again, picking one of the buses, bus number K, we can say that, and this is power going into that bus, so we should remember that. Pk plus Jk, Q sub K, that's the complex power that is going into that bus, okay? That's the convention, and that's equal to this voltage at that bus times the conjugate of the current that is going into that bus, right? So we know that the current that goes into that bus can be written in terms of voltages by this equation, where Ykm, the admittance, consists of the conductance part and the susceptance part over here. And these voltages can be written in their polar form like this, magnitude and the phase angle, right? Similarly, at any other bus M over here. So if you substitute all these into this equation on the top, we can then come up with one equation for power and one equation for reactive power. Okay, and we're not trying to derive these over here. They are in the textbook in this chapter number 5. Okay. All right. So we know that we need to solve these equations, and these equations are nonlinear because power, the load on these buses, for example, is specified as power and reactive power. Okay. If it was specified as purely constant impedances, then perhaps we could have solved it much easier way. But they become nonlinear. So we have to solve these equations for bus voltage magnitudes and phase angles, because if we can calculate the voltages at all the buses in terms of magnitude and phase angles, then we can solve everything, right? Then we can solve the power flow. So that's what we are looking for. What are the magnitudes of these voltages at these n buses, and what are their phase angles? So that's what we have to solve. So let's count the number of unknowns that we have. Well, we have, first of all, n PQ. So that's the number of PQ buses we have. Okay, so at all these PQ buses, we don't have the voltage magnitude. So we have these many unknowns over here in terms of voltage magnitudes. But when it comes to voltage phase angles, we don't know them at PQ buses, and we also don't know them at PV buses, because at PV buses, the voltage magnitude is specified. That's why this n sub PV does not show up over here, but it shows up over here, right? So if you add these two up, we have 2 times the number of PQ buses plus the number of PV buses. So those are the unknowns that we have. And the same number of equations will show up, as you can see here, because P is specified at PQ buses and also at PV buses, and similarly Q is specified at PQ bus over here. So if you add these two, all these three, I should say, we come up with this number over here. Okay, so we have the same number of unknowns as we have as the number of equations that we have. Otherwise, we won't be able to solve this problem. Okay. All right. So basically, there are 2 procedures. One is this Gauss-Seidel procedure, which is not used very much. It's used once in a while, but we should at least be aware of it, that it exists. Okay. So let's look at this Gauss-Seidel procedure. I will not go into the detail because it's also not covered in our textbook, but there are many other books you can go to and look them up. Okay. So what is this Gauss-Seidel procedure? Well, we know that this complex power can be defined like this: voltage times current conjugate, right? So from this equation, the current can be calculated as, this was conjugate here, so here we don't have the conjugate. So instead of plus sign, this becomes a minus sign over here, and then we have voltage conjugate in the denominator over here. So, so now this current, which is written in the right-hand side here, can be given by, this using that admittance matrix that we talked about in terms of the voltage at that bus and the voltages at other buses like this here. Okay, so we have this equation, and this equation can be solved for V sub k in this form here. So if you take this equation on the top, let me erase all this ink that I have here. This equation here can be solved for this voltage in this form here. Okay, and similarly, the reactive power can be calculated from this equation. So what one has to do in this Gauss-Seidel procedure is we have to iterate on these voltages on all these buses until the change in the voltage magnitude and the phase angle is below a certain tolerance. Okay, so we just have to iterate. So that's the Gauss-Seidel procedure, and as I mentioned to you, it is used sometimes. But for the most part, we use most of the commercial software, and that's why we have chosen to concentrate on this, this Newton-Raphson procedure. So what is this Newton-Raphson procedure? Well, we know that except for the slack bus, all the other types of buses, power is specified, right? And this power can be written in terms of the voltages at all these buses here, in terms of their magnitude and in terms of their phase angles. Okay, so that's what this equation is showing here. Similarly, at PQ buses, the reactive power is specified, and this reactive power can be expressed in terms of the voltages of all these N buses, right? So if we have the exact solution for all these voltages in terms of magnitude and phase angles, then the right-hand side should be equal to 0. Whatever is specified is what you're calculating, right? So the difference between the two should be 0 for power as well as for reactive power. So this is the type of equation or equations that we will go and solve in this Newton-Raphson procedure. And since these are nonlinear equation, they are sort of, you can call them trial and error procedure. Okay. So again, you see that we have this number of equations, this coming from the PV buses where power is specified, and these coming from PV and PQ buses here. So because here power is specified and the phase angle is specified, power is specified and the reactive power is specified, that's why this factor of 2 here comes in, where only power is specified over here. So we have this many equations, and we earlier agreed that that's the same number of unknowns that we have to solve. Okay. So a very simple explanation of this Newton-Raphson procedure. Okay. So let's take a case where we have an equation like this, where let's say C is a constant here. And then we have a function of x, and we have to solve for x in this equation here. Okay. So let's make an initial guess and say that this is x0. And when we plug this in for x here, this is, again, this symbol doesn't come through. It's approximately equal to 0, because that's an initial guess, which may not be correct. Okay. So if you plug that in for x, and of course you can say that you have some deviation from this x to make it as close to 0 as possible, but that again is an approximation. So that's why that approximate symbol. So our purpose here is to calculate what this delta x is. So we can write this equation by Taylor series expansion, and we will neglect the higher order terms. We'll just take the first order term. So this is given by what you see here in the bracket, this function at x0 plus the partial of this function at x0 times delta x. So this equation gives us this one over here, and we can rewrite this equation in this form, from which we can say that this delta x is equal to this divided by this partial over here. Okay, so from here we can calculate this delta x, and then we can add that to our initial guess, and that becomes our next estimate of x, right? And we apply the same procedure as before, and we calculate the next value of delta x, and when we add that to our guess x1 over here, that becomes the value for the next try. Okay, so we keep on doing this until the difference here is below some tolerance limit. Okay, and you can make that as small as you want. Okay, so we can see this with a very simple example here. 4 minus x squared equal to 0. Okay, so the answer here is obvious. Okay, that x is equal to 2 when we solve this equation, right? So we already know the answer, but let's see how Newton-Raphson procedure would converge to this answer. So we initially guess x to be 3.5. Obviously, we know it's wrong, but applying that procedure, it gives this next value of x to be about, I think it's in the textbook, but about 2.3 or something like that. And if at that value, again calculate what the next guess would be, it brings us very close to 2. Okay, and if that's good enough, that's our answer. Something very close to 2 here, if it's within the tolerance limit. So that's how this Newton-Raphson procedure works. All right. So we are going to apply this to this power system problem. And again, we are talking about this n-bus system, general. All right. So here I'm repeating this equation for power and reactive power at bus K that we saw earlier. And now what we have to do is to take partial of these equations with respect to angle and voltage magnitude. So that is what is done here. Here you see, I'll not go into how you go about doing it. It's pretty straightforward, except you have to be very careful. Okay, very easy to make mistakes. So I think, but there's no mystery here, and it shows that you can take partial of power with respect to phase angle, and this is power at the same bus as the phase angle, whereas the power at bus K or the phase angle at some other bus where J is not equal to K. So this completes this set, and similarly we can do for differential of power with respect to voltage magnitude. So it will give us these two equations, and we can then go on and do whatever we did for real power for reactive power over here. So partial of reactive power and partial of with respect to phase angles here, and partial of reactive power with respect to voltage magnitudes over here. Okay, so it's just a matter of being carefully finding these partials and writing them down. But in a n-bus system, you have to form a procedure to come up with these partial derivatives over here, whereas here we are doing it manually one at a time. But the bottom line is that after having done all that, we have a Jacobian matrix like this here, okay, which is telling us is that we have these unknowns here, the phase angles of the buses. And these are all matrix equations, and the voltage magnitudes, the changes in those we need to make from one iteration to the next, and multiplying these with this Jacobian, which consists of this differential of power with respect to angle, differential of power with respect to voltage, and similarly reactive power with angle and reactive power with respect to voltage here. So that's our Jacobian matrix, and multiplying it by these deviations that we need to compute in order to converge on the right solution, what we see here is that it should be the difference between the power that is specified and the power that we calculate using expressions of this type, and similarly reactive power that is specified minus the reactive power that we calculate using this expression over here. Okay, so this is our matrix, and in order to solve these correction terms that we need in phase angle and voltage magnitudes, these deltas, we need to solve this equation over here. Well, we can write this down as inverse of this Jacobian times the difference between specified minus the computed using the two equations on the top. Now, how do we compute this inverse of this Jacobian when it's a 10,000 by 10,000 matrix, okay? If you happen to have 10,000 buses, and that's not very uncommon, okay? So in order to do that, we do this optimal ordering and apply sparsity techniques. But those are really beyond this first course that we are talking about. So here in this example, we'll invert them in a very general, usual manner, which you cannot do when you have 10,000 by 10,000 as the number of elements in this matrix. And by the way, this Jacobian keeps changing from one iteration to the next. Okay, so it's not a constant matrix. Okay, so that's a challenge that is met, as I said, using optimal ordering of these buses and sparsity techniques. But if you have this inverse, then multiplying it by this difference on this right-hand side, we can calculate the correction that we need to make in phase angles and voltage magnitudes to go to the next iteration till the whole process converges within a tolerance limit. Okay, so it's very clear that we really want to make this difference here, equal to 0. So long as within a tolerance limit, we say it's good enough. Okay, and that's our solution.